This lesson on materials has a lot of definitions and a lot of concepts, no math. It's kind of different than what we've been doing. So we're going to start with just some descriptions of the phases of matter. And so just remember, we're going to make sense out of a lot of these. So in a solid, the particles are packed closely together and they're kind of locked in place. An atom that is, like right here will stay there. It won't kind of work its way over. Unlike a liquid, they are pretty far apart, and a molecule or an atom that's on one side can work its way to the other side. They're moving around. They're sliding past each other in contact with each other. In a gas, of course, they're very, very far apart, and there's little interaction. Remember, this is not to scale at all. These particles are very small compared to the space between them. But in all three cases, the particles are moving, and that's because we're not at absolute zero. So even in a solid where they're locked in place, they're vibrating in place. Okay. The other thing is that in all three cases, there are attractions between particles. In the case of the solid, that's what keeps it locked in its place, is the fact that it's attracted to its neighbors. They stick together. Same thing with a liquid. The attractions may not be quite as strong, but they do keep them in contact. That's why it's a liquid. And I know that a lot of times we say, for an ideal gas, we acted like these particles are not attracted to each other. The truth is they are. We made that assumption that the attractions are very weak, and they're so far apart that attraction doesn't take hold, so they don't all stick together. Keep in mind that if attractions are really strong, then everything would be a solid. And so we're going to pay a lot of attention to those attractions, because they not only determine if something's a solid, liquid, or gas, but they also determine things like boiling point, whether or not something dissolves in something else, and so forth. So some other terms that we need to know, when we say fluid, what does that mean? It just means that it can flow, and so that includes both liquids and gases. When we say compressible, in general, that's just gases. And when we say a condensed phase again as liquids, but also solids. Okay, so we're going to talk a lot about those attractive forces. And when we say this, we're talking about attractions between different particles, not within one particle. And so keep in mind that we're not talking about these bonds on the water. Those are intra-particle attractions. So covalent bonds are within one particle. This is one particle, one molecule. Here's another one. So we're talking about these attractions that occur in here. What holds one molecule to another molecule? And the way to think about this is, the stronger these attractions are, these are what would hold it into the solid. Okay. Anyway, so you need to know this order of the types of attractions. In an ionic solid, that is what holds them into a solid, is the ionic bonds, and that's the strongest type of attractive force. Hydrogen bond is going to be the strongest type for a covalent compound, and then there are dipole, and London dispersion forces. Sometimes people group these, like they'll say van der Waals, and it includes several of these and stuff like that. But so just be aware, sometimes the naming is a little bit different in how they say it. But dispersion is probably the most common for this London. So anyway, we've got a trend here that the stronger the attractive forces, the more likely it is to be a solid and a higher boiling point. So boiling point is how hot you have to heat it for the particles to come apart and become a gas. Also, we'll be looking at surface tension and vapor pressure as other properties. We'll talk about each of those properties. Okay, let's just go through each type of interparticle attractions and what causes them. And of course, in an ionic bond, we're talking about these are full charges. And what I mean full versus partial, because polar compounds have partial charges. The full charges, positive and negative attracting, this is, in other words, like +1, -1, +2, -2. Those charges really lock these ions in place. And this is why most ionic compounds are solids. Okay, then if you're going to look at covalent compounds, and by the way, this is not in order of strength on purpose, but dipole-dipole is kind of a medium attraction. Dipole-dipole is caused by polar bonds. So a polar bond, remember these two electrons that are being shared here, those two electrons that are being shared, they may spend more time with one atom. And because chlorine is more electronegative, has a stronger pull, those electrons are spending more time with that chlorine. So that's why we have this, this lowercase delta with the charge. That means a partial negative charge. It's slightly negative. For the same reason, this hydrogen is slightly positive. The electrons are spending more time with chlorine. And so here are our two molecules. And so there's an attractive force in here because positive and negative ends attract. And so they line up. Okay, so that's an attractive force based on partial charges. It's not as strong as the ionic bond. Let's look at hydrogen bonding because this really is kind of a type of dipole-dipole attraction. It's just that it's so strong that they kind of put it in another category. And it also involves some lone pairs, thinking about what happens with some lone pairs. So let's just look at it with water, because water is a common example. Water has some polar bonds, and so we have that usual setup here with the partial charges. So that hydrogen has a slightly positive charge. The thing is, if you notice the dots, the dots are the hydrogen bond. It's attracted to this lone pair here. So we know about Lewis dot structures, and we know about this molecule. It has this shape, and it has these lone pairs that stick out. Well, those are really sticking out, and you know, a lone pair of electrons is awfully negative, so this hydrogen is attracted to the lone pair. It makes this, because this bond is really one of the most polar bonds, and because of the lone pairs, it makes the hydrogen bond extra strong compared to a regular dipole-dipole attraction. So you can, this is the most common setup, but you can have this kind of setup anytime you have this arrangement. Oops. Where X and Y are either nitrogen or oxygen, and they could be one of each, like a nitrogen and then an oxygen, and or fluorine. Fluorine's a little bit less common. So in all of these cases, this bond will be very polar, and this atom will have a lone pair that hydrogen is attracted to. Okay. And so to decide if a molecule has this, you can just look at the structure and look for these bonds. If a molecule has one of those, then we know that the molecules can hydrogen bond to each other. And I really want to emphasize, this is what gets people. This is not a hydrogen bond. The hydrogen bond is between molecules. Okay. Okay, let's look at, oops, we skipped, nope. Yep, I didn't finish this slide. Okay, dispersion attractions. That's our last type of attractions. Dispersion forces, sometimes called London dispersion forces, induced dipole, a couple of different ways this is said. I've really exaggerated this, but what's happening is that we have an atom, and this in the center is its nuclei. Of course, the nuclei has a positive charge because of the protons. And what's happening is because the atom is always in motion, even if it's vibrating in place, it can get off center. Just slightly off center, and just for a very, very, very short time. But it can get off center. And when it does, that's how you get these positive charges on this end, because the nucleus is making this end a little more positive. And of course, you have a little bit more negative on this end. And these, of course, are very, very small charges, but they're still there. And so what happens is if this one becomes a little positive on this end, it attracts the electrons from this one. And so it can kind of cause that one to get off center and so on. So it's a chain reaction. And, you know, it's just a matter of they're all shifting together all the time very fast. And so it causes a basic stickiness between atoms. And if you have two molecules, they may have two atoms in contact. So that's the best way to think about it, is that atoms are kind of stick to other atoms if as their electron clouds shift around. Okay, one more thing about dispersion attractions is that they're pretty weak, but they can come into play depending on the size of your atoms. If the atoms are larger, then they can get more off center. So when you have a small atom, we say those electrons are held more tightly. But when you have a large atom, what happens is these atoms on the outside are not held as tightly, and so it can it's kind of more wobbly, and it can become more polarized, we say, because those electrons are further from the nucleus, so we say they're held less tightly. Okay, what about molecule size? Well, on molecules, so I should circle that too. On molecules, the larger the molecule matters also because there are more atoms touching. And so, you know, if you have a molecule that, you know, has 5 atoms versus one with 2, let's just say like this. If some of these get together, they may have 2 atoms touching at once. But if this is near another molecule like it, they may have 3 atoms touching at once. So the bigger the molecule is, the more stickiness they can have when they come up to another atom or another molecule. So for example, on this one, which has stronger attractions, these are bigger atoms, so they would be more polarizable, like we were saying up here. And then there's a big difference here. These are much bigger. 2 of these molecules would be really long. They could probably have 10 or more atoms in contact at one time, and so lots of contact. These may have 2 or 3 atoms in contact at one time if there are a bunch of those around.